We're going to be reading Chapter 9, Section 1, Surface Water Movement. Earth's water supply is recycled in a continuous process called the water cycle. Water molecules move continuously through the water cycle following many pathways. They evaporate from a body of water or the surface of Earth, condense into a cloud droplets, fall as precipitation back to Earth's surface, and soak into the ground. As part of a continuous cycle, the water eventually evaporates back into the atmosphere. Again, form clouds, again, fall as precipitation, and so on. Understanding the mechanics of the water cycle helps to explain the reasons for variations in the amount of water that is available throughout the world. Often, a water molecule's pathway involves time spent within a living organism or as part of a snow-filled glacier, lake, or ocean. Although water molecules may follow a number of different pathways, the movement process is one of repeated evaporation and condensation powered by the sun's energy. What happens once water reaches Earth's surface? Does all the water sink into the ground or evaporate? Runoff. As shown in Figure 9.1, precipitation falls on Earth's surface in the form of rain, snow, sleet, or hail. In most instances, solid forms of precipitation, such as snow, sleet, and hail, may eventually melt, or they can also be incorporated into the mass of a glacier. Once water reaches Earth's surface, it can evaporate into the atmosphere, soak into the ground, or flow down slopes on Earth's surface. Water flowing downslope along Earth's surface is called runoff. Runoff may reach a stream, river, or lake, may evaporate, or in many accumulate as puddles in low-lying small depressions and eventually seep into the ground. During and after heavy rains, you can observe these processes occurring in your own yard or local park. Water that seeps into Earth's surface becomes groundwater. A number of conditions determine whether water on Earth's surface will seep into the ground or become runoff. For water to enter the ground, there must be large enough pores or spaces in the ground surface materials to accommodate the water's volume, as in loose soil illustrated in Figure 9.2a. If the pores already contain water, the newly fallen precipitation will either remain standing on top of the ground, or, if the area has a slope, run downhill. Water standing on the surface of Earth eventually evaporates or flows away. Vegetation. Soils that contain grasses or other vegetations allow more water to enter the ground than do soils with no vegetation. Precipitation falls on vegetation slowly, flows down leaves and branches, and eventually drops gently to the ground. In contrast, precipitation falls with far more force into barren land. In such areas, soil particles clump together and form dense aggregates with new pores or spaces between them. The force of falling rain may then push the soil clumps together, thereby closing pores and allowing less water to enter, as illustrated in Figure 9.2b. This is why gardeners do not pack the soil under their plants. Compacting the soil reduces the space between the particles that are available for water to seep in, thus reducing the amount of water that is available to the plant's roots. Rate of precipitation. Light, gentle precipitation infiltrates the dry ground. However, the rate of precipitation may temporarily exceed the rate of infiltration. For example, during heavy precipitation, water falls too quickly to soak into the ground and becomes runoff. Thus, a gentle, long-lasting rainfall is more beneficial to plants and causes less erosion by runoff than a torrential downpour. If you have a garden, remember that more water will enter the ground if you water your plants slowly and gently. Soil composition. The physical and chemical composition of soil also affects its water holding capacity. Soil consists of decayed organic matter called humus and minerals. Humus creates pores in the soil, thereby increasing a soil's ability to retain water. The minerals in soil have different particle sizes, which are classified as sand, silt, or clay. As you learned in Figure 7, the percentage of particles of each size vary from soil to soil. Soil with a high percentage of coarse particles, such as sand, has relatively large pores between its particles and allow water to enter and pass through the soil quickly. In contrast, soil with a high percentage of fine particles, such as clay, clumps together and has few or no space between the particles. Such small pores restrict both the amount of water that can enter the ground and the ease of movement of water through the soil. Slope. As you have learned, the slope of land area plays a large role in determining the ability of water to enter the ground, as shown in Figure 9.3. Water from precipitation falling on slopes flows to areas of lower elevation. The steeper the slope, the faster the water flows. There's also greater potential for erosion on steep slopes. In areas with steep slopes, little water seeps into the ground before it runs off. Stream systems. Precipitation that does not enter the ground usually runs off the surface quickly. Some surface water flows in thin sheets and eventually collects in small channels. As the amount of runoff increases, the channels widen, deepen, and become longer. Although it is common for these small channels to dry up shortly after precipitation stops, the channels again fill the water each time it rains and become larger and longer. If a sufficient supply of water develops, the water begins to flow more permanently in a channel and can become a stream. All streams flow downslope in a water path to lower elevations. However, the power of the stream can vary considerably depending on the slope of the land and the type of material through which the streams flow. Some streams flow into lakes, while others flow directly into the ocean. Still, others called tributaries flow into other streams, as shown in Figure 9.4. Each tributary increases the size of the stream it is joining and adds water to it. A large stream is called a river, and its tributaries make up a stream or river system. Small streams are called brooks and creeks. If there are any brooks or streams near your home, you can locate where they feed into other streams or lakes. Watersheds and divides. All of the land area whose water drains into a stream system is called the system's watershed or drainage basin. Watersheds can be relatively small or extremely large in area. A divide is a high land area that separates one watershed from another. Each tributary in a stream system has its own watershed and divides, but they are all part of the large stream system to which the tributary belongs. The watershed of the Mississippi River, shown in Figure 9.5, is the largest in North America. Stream load. All the materials that the water in a stream carries is known as the stream loads. The living components of water include microscopic life forms, as well as large plants and animals. The non-living components of surface water include sediments, dissolved solids, and dissolved atmospheric gases such as oxygen. There are 3 ways in which a stream carries its load. Solution. Material is carried in solution after it becomes dissolved in the stream's water. How much of the stream's load is carried in solution depends on the material through which the stream's water has passed. Then, when water runs through or over rocks containing soluble minerals, it dissolves small amounts of minerals and carries them away in solution. Water may readily dissolve calcium carbonate from limestone and marble, for example. Streams also commonly carry soluble magnesium compounds. Groundwater adds most of the dissolved load to stream water, while runoff adds only a very small amount. The amount of dissolved material that water carries is often expressed in parts per million, or ppm, as shown in Figure 9.1. For example, a measurement of 10 ppm means that there are 10 parts of dissolved water for every 1 million parts of water. The total concentration of materials in solution in streams average 115 to 120 ppm, although some streams carry as little dissolved materials as 10 ppm. Values greater than 10,000 ppm have been observed for streams draining desert basins. Measuring the amount of mineral in solution helps scientists monitor water quality. Suspension. All particles small enough to be held up by the turbulence of a stream's water moving are carried in suspension. Particles such as silt, clay, and sand, they are carried in suspension as part of a stream's suspended load. The amount of mineral in suspension varies with the volume and velocity of the stream water. Rapidly moving water can carry large particles in suspension than slowly moving water. As the velocity of the water decreases, the heavier particles settle to the bottom, as you can see by doing the problem-solving lab on the next page. Bed load. Sediments that are too large or heavy to be held up by turbulent water and transported by streams is another matter. A stream's bed load consists of sand, pebbles, and cobbles that the stream's water can roll or push along the bed of the stream. The faster the water moves, the larger the particles it can carry, both in suspension and as part of its bed load. As the particles move, they rub, scrape, and grind against one another or against the solid rock of the stream bed in a process called abrasion, the wearing away of a solid earth material. This action contributes to the physical weathering of the stream's bottom and sides. and it provides an additional source of material to be eroded by the stream, either in the solution or at part of the suspended load. As gravity pulls stream water to lower elevations, the stream's load moves along with the water. The moving water continuously tosses and tumbles on the weathered material, whose pieces become smooth and rounded over time. As shown in Figure 9.6, most pebbles along the bottoms and sides of streams are round and polished as a result of this process. Bed load sediments not only wear away one another, but they also abrade the surface of the stream bed. Potholes may form at the bottoms of streams where pebbles have continued to swirl around in one area and have slowly worn holes into solid rock. For example, potholes more than 3 meters deep have formed near Little Falls, New York, in the Mohawk River Valley. Potholes can be found even in the stream beds exposed of very hard exposed bedrock. The huge depressions in the stream bed of the Wisconsin River, shown in Figure 9.7, were scoured out of granite. Large stream bed potholes dramatically illustrate the powerful abrasions caused by a stream's bed load. Stream velocity and carrying capacity. The ability of a stream to transport material, referred to as its carrying capacity, depends on both the velocity and the amount of water moving in the stream. Study Figure 9.8 as you read. The channel's slope, depth, and width all affect the speed and direction in which water moves within. A stream's water moves more quickly where there is less friction. Consequently, smooth-sided channels with great slope and depth allow water to move most rapidly. The total volume of moving water also affects a stream's carrying capacity. Discharge is the measure of the volume of stream water that flows over a particular location within a given period of time. Discharge is commonly expressed in cubic meters per second, meters squared s, m3s. The following formula is used to calculate the discharge of a stream. Discharge equals width times depth times velocity. The largest river in North America, the Mississippi, has a huge average discharge of 173,600 meters cubed. However, the Amazon River, the largest in the world, has an incredible discharge 10 times that amount. This discharge from the Amazon River over a 24-hour period would supply New York's water needs for 9 years. As a stream's discharge increases, the stream's carrying capacity increases as well. The increased discharge results in a stream with greater carrying capacity as modeled in the GeoLab at the end of the chapter. Both water velocity and volume increases during times of heavy precipitation, rapid melting of snow, and flooding. In addition to increasing a stream's carrying capacity, these conditions heighten a stream's ability to erode and land over which it passes. As a result of an increase of erosional power, a stream bed can widen and deepen, thereby increasing the stream's slope and further adding on to the stream's carrying capacity. As shown in Figure 9.9, the extraordinary power of water during such times can be especially hazardous for people who do not anticipate the dangers associated with flooding. Flood plans. The amount of water being transported in a particular stream at any given time varies with weather conditions. Sometimes more water pours into a stream than the banks of the stream's channel can hold. A flood occurs when water spills over the sides of a stream banks onto the adjacent land. The broad, flat area that extends out from a stream's bank and is covered by excess water during times of flooding is known as a stream's floodplains. Flood water carries along with a great amount of sediment eroded from Earth's surface and the sides of the stream channel. As floodwater recedes and its volume and speed decreases, the water drops its sediment load onto the stream's floodplain. Floods. Floods are natural occurrences. When a stream reaches its flood stage, a flood can occur, as shown in Figure 9.11. Flood stage is the level at which the stream overflows its banks, and the crest of the stream is the maximum height. Because it takes time to run off to collect in streams, the water continues to rise and may reach its crest days after precipitation ends. The resulting flooding may occur over localized small areas or across large regions. The flooding of a small area is known as upstream flood. Sudden rainstorms that drop large amounts of rain within a short period of time cause upstream floods, as do dam failures. Although they are localized, upstream floods can do a great deal of damage within a very short period of time. Heavy accumulations of excess water, form large regional drainage system results in downstream floods. Such floods occur during or after long-lasting intense storms or spring thaws of large snowpacks. The tremendous volumes of water involved in a downstream flood can result in extensive damage. For example, the devastating floods in 1993 along the Mississippi River, which frequently cause downstream flooding, left landscape scars that are still visible today. Flood monitoring and warning systems. In an attempt to provide warnings for people at risk, government agencies monitor potential flood conditions. The National Weather System monitors changing weather conditions. Earth's orbiting weather satellite photograph Earth and collect and transmit information about weather conditions, storms, and streams. In addition to the U.S. Geological Survey, it has established gauging stations as shown in Figure 912 and on approximately 4,400 streams in the United States. This gauging system stations provide a continuous record of water level in each stream. Technological advances have made it possible for anyone with internet access to obtain real-time data on streams through government-sponsored websites. In areas that are prone to severe flooding, warning systems are the first step in implementing emergency management plans. Flood warnings and emergency plans often allow people to safely evacuate an area in advance of a flood.